Have you ever wondered what engineering is all about? It's a fascinating field that's all about designing, building, and maintaining everything from the smallest gadgets to the largest structures. It's the application of scientific principles and mathematical methods to create solutions that work in the real world. Engineering isn't just about equations and blueprints. It's about creative problem solving. It's about looking at a challenge and thinking, how can I make this better? How can I make this work? It's about using a systematic approach to solve problems, taking into account factors like feasibility, cost, safety, and sustainability. Imagine having an idea and then being able to bring that idea to life, to see it working, to know that it's making a difference. That's what engineering is. It's a process of continual learning and improvement, of pushing boundaries and making things happen. That's the magic of engineering. It's about making ideas work in the real world. The first step in the engineering process is to identify the problem or need. Now, this might sound simple, but it's a crucial part of any engineering project. It's like setting the coordinates for your journey. Without knowing your destination, how can you plot the course? In this step, we don't just name the problem. We dive deep into it. We ask questions, poke it from all angles, and try to understand it as thoroughly as possible. What challenge are we trying to solve? What opportunity are we trying to seize? Remember, a well-defined problem leads to a relevant and effective solution. So we aim to be as specific, clear, and comprehensive as we can. We consider various factors like feasibility, cost, safety, and sustainability. In essence, this step is about laying a solid foundation for our project. It's about understanding the why behind our what. Once we define our problem, we can start to think about potential solutions. With a clear problem in mind, we enter the research phase. This step is all about gathering information and understanding the intricacies of the issue at hand. It's akin to assembling the pieces of a puzzle. The more pieces you have, the clearer the overall picture becomes. This often involves studying existing solutions, consulting with experts, and deep diving into the relevant scientific principles and engineering standards. Consider this phase as the reconnaissance mission before the main operation. It's about exploring the problem landscape, identifying potential constraints, and understanding the rules of the game. You're not just looking for what's been done before. You're also hunting for gaps and opportunities for innovation. This knowledge will be your ammunition, helping you to design a solution that's not just feasible, but efficient and effective. Moving on, armed with this wealth of information, we step into the realm of design. This is where the magic happens, where your creativity meets practicality. It's where you take all that you've learned and use it to craft a solution. This might involve sketching ideas on paper, creating digital models, or even building physical prototypes. Design in engineering is a delicate balancing act. It's about reconciling the demands of functionality, cost, safety, and sustainability. It's about finding the sweet spot between what's desirable, what's viable, and what's feasible. It's about translating abstract concepts into tangible solutions. It's not just art, it's a science in its own right. And just like any science, it's iterative. You sketch, you model, you prototype, you test, and then you refine. You repeat this process until you have a design that not only looks good on paper, but also stands up to scrutiny in the real world. In essence, the research and design phases are the heart and soul of the engineering process. They're where problems are understood, solutions are imagined, and plans are laid out. They're where science meets creativity, where knowledge meets innovation, and where ideas take shape. A well-researched design is our blueprint for success. It's the roadmap that guides us from the realm of ideas to the land of reality. It's the bridge that connects problems to solutions, needs to fulfillments, and dreams to achievements. But even the best designs need testing. And that's where our fourth step in the engineering process comes into play: analyzing and testing the design. This step is all about making sure our solution is as robust and efficient as possible before we start building it in the real world. First off, we kick things off with an in-depth analysis of our design. We're looking for any potential weak spots or areas for improvement. We want to ensure that our design is not just good, but great. We're looking at the minutiae, the tiny details that can make or break the success of our solution. We're considering every angle, every variable, and every potential outcome. Now, how exactly do we do this? Well, there are a few tools in our engineering toolbox that can help. Computer simulations, for instance, allow us to test our design in a virtual environment. We can simulate different conditions, apply various loads and forces, and see how our design responds. This gives us a good idea of how it's going to perform in the real world, without the cost or risk of physical testing. But sometimes, there's no substitute for the real thing. That's where physical testing comes in. This might involve creating a prototype and putting it through its paces, or it might mean testing individual components to make sure they're up to the task. Either way, the goal is the same: to ensure that our design can withstand the rigors of its intended use. Now, once we've analyzed and tested our design to our satisfaction, it's time for the fifth step: building or implementing our design. This is when we take our meticulously planned design and turn it into a tangible, functional solution. It could involve construction, fabrication, programming, or any number of other processes, depending on the nature of our project. This step is all about precision and attention to detail. We're taking our design from the realm of the theoretical and making it a reality. It's a thrilling stage of the process, filled with anticipation and excitement. After thorough testing, it's time to bring our design to life. And that, my friends, is the magic of engineering. The ability to take a concept, an idea, and transform it into something real, something that solves a problem or fulfills a need. That's what makes engineering such a rewarding field to be a part of. Now we have a working solution, but our job isn't over yet. The final step in the engineering process is perhaps the most crucial one, and that's evaluation and iteration. This step is all about assessing the performance of your solution and refining it further. It's about asking questions like, is the solution achieving its intended purpose? Are there any unforeseen issues? Can it be optimized for better performance? By evaluating your solution, you can identify areas for improvement and make necessary adjustments. This step isn't a one-time thing either. It's a constant cycle of feedback and improvement. You see, in engineering, there's always room for enhancement. There's always a way to make something more efficient, more cost-effective, more sustainable. And that's the beauty of engineering. It's not just about coming up with solutions, it's about continuously striving for better ones. Remember, engineering is a continuous process of innovation and improvement. Engineering is a vast field with many specializations. It's like a tree with many branches, each one reaching out to solve different problems and create new possibilities. Let's explore some of these branches, shall we? First, we have civil engineering. This is the branch that deals with the design, construction, and maintenance of infrastructure. Think buildings, bridges, roads, and dams. If you've ever wondered who's behind the structures that make up our cities and towns, that's civil engineering at work. Next, we have mechanical engineering. This is all about the design, analysis, manufacturing, and operation of mechanical systems. If it involves engines, machines, and robots, chances are a mechanical engineer had a hand in it. Then there's electrical engineering. This branch deals with the design, development, and application of electrical equipment, systems, and electronics. From power grids to smartphones, electrical engineers keep our world connected and powered up. Chemical engineering applies the principles of chemistry and physics to the development and production of chemicals, fuels, and other materials. They're the masters of reactions and transformations, making things happen on a molecular level. Computer engineering, on the other hand, combines electrical engineering and computer science to design and develop hardware and software systems. They're the architects of the digital world, building the machines and systems that drive our modern life. Software engineering takes this a step further, applying engineering principles to software development. They're focused on creating reliable, maintainable, and efficient software systems, from the apps on your phone to complex computer networks. Biomedical engineering merges engineering with biology and medicine. They design devices and systems for healthcare applications, helping to improve lives and health outcomes. Aerospace engineering is all about the design, development, testing, and operation of aircraft and spacecraft. If it flies or orbits, an aerospace engineer was likely involved. And finally, we have environmental engineering. This branch uses the principles of engineering, soil science, biology, and chemistry to develop solutions to environmental problems. They're the defenders of our planet, working to keep our environment clean and sustainable. So, whether you're interested in buildings or biomechanics, there's a branch of engineering for you.